Welcome to COSM 2023. Thank you. I'm Steve Bury, the president of Discovery Institute. Our Walter Bradley Center for Natural and Artificial Intelligence puts on this program each year, and it's become a crowd favorite. George Gilder is our inspiration. He's the co-founder of Discovery Institute, a longtime senior fellow, and I know that you're going to learn a lot over the next 3 days. Please join me in welcoming Matt McElwain, Managing Director, Madrona Venture Group.
You know, we could go all the way back to my alma mater, Dartmouth College, which in 1956 had the first summit on artificial intelligence. And we can trace a whole series of waves of highs and lows. And so there's an understandable question of, well, why is it going to be that different this time? And I think it might be helpful to all of you, since the predominant theme of the next couple of days is what is going on in the world? Why has there been such a breakthrough in the last year, particularly at least in the eyes and the minds of the end user, because of this thing called generative AI as a next step forward in the applied AI, world. And so I want to unpack that a little bit. And in order to understand where we're at in this last year, it's probably useful to think back just even at the last 10 years. Something called AlexNet came upon us in 2012, and that was the first attempt to apply deep learning in a systematic way to be able to understand and recognize images more effectively. Around the same time, we at Madrona invested in a company that was founded by the Amazon professor of machine learning at the University of Washington. That was a company that came to be known as Turi. It was eventually bought by Apple. And they were also taking some of these machine learning and deep learning techniques. So that's a decade ago. And I think most people would look back and say that that was the beginning of this next wave. Believe it or not, it was January 2014 when Google acquired DeepMind. Many of you are familiar with some of the, AlphaGo and AlphaFold. I'm sure we're going to talk a bit about the application of life sciences over the course of the next few days with some of the folks I know that are in the room. That was the next big milestone. And then there's OpenAI. That was 2015. That was 8 years ago as well. In fact, one of the little irony points about OpenAI is that it was originally founded as a nonprofit, and one of the first investors was actually Amazon as a contributor to the nonprofit side of it. When it went for profit was when Microsoft got involved. So we'll hear both from people from Amazon and Microsoft today, of course, both of them deeply embedded in the AI world. But through this period of time, and we can add maybe one more key milestone, when the Attention is All You Need paper was published by the Google team in 2017, the BERT model, first generation there. This is an era, all pre-2020, of what we would just consider kind of a research-oriented and an academic-oriented phase around what we think of as deep learning into foundation models and generative AI. And it's really only been in the last 3 years, and to give them credit where credit's due, where OpenAI has taken some of these ideas and applied them to the various GPT models, the generative pre-trained transformer models. GPT-3 was launched in 2020. So that's just 3 years ago. And so we've had this kind of short intermezzo era that you see in the middle where scaled model development and delivery has been the focus. Of course, not just for OpenAI, which one might argue, I would argue, is not so OpenAI. But there are a lot of other players, like Stability AI and Stable Diffusion, like Llama 2, and Llama 1, and then Llama 2 from our friends at Meta, Facebook, and on and on and on, that are far more open as open models applied to AI. And by open here, we really mean at least 3, you could argue more, dimensions to it. One is, what's the data you're using? How open is the data and the metadata that is fed into some kind of a model? Second, how open is the model, and how flexible can the model be in terms of being able to modify some of the parameters in the model? modify some of the, the areas of tuning. And yes, in some cases, including, in most cases, there's some access to doing so-called fine tuning, but there's more restrictive versions of that, and there's more open versions of that along a spectrum. And then thirdly, you've got this notion of open evaluation. How transparent and open is it because as we'll see in a second, the key to generative that is different is that we move from largely a deterministic state to a somewhat non-deterministic state or predictive state in terms of how we think of building applications. And with that change, we need to be able to evaluate what's coming out of the system and how transparently it comes out of the system. And so our view is that we're about to come upon a massively, prolific era of application building. And at the end of the day, nobody's really building a model just for model's sake. They're building a model or a cocktail of models to build the next generation of intelligent applications across a broad spectrum, whether that's financial services, life sciences, whatever it might be. That sets us up for this slide. This is a hopelessly busy slide, and I'm going to abstract it to hopefully help it be a little bit more useful, again, in framing the discussions throughout the next couple of days. If we look at the person and the device on the far end of this, there's three things to keep in mind that are different about this generative and what might even become sort of the post-generative era. First of all, is I'm using natural interfaces to interface with the system. The system is everything that's in the darker blue. Now, the most popular natural interface at the moment is typing. I can type something in to query this system or to interact with this system, prompt the system. But what about voice? Or what about images? Of course, those can all be prompts too. And they will be prompts, and they are prompts in different use cases already. And why does it have to be a human that's interfacing with the system? It could be the device, which is why the device is in this picture. So there's a transformation that's happened because of the different interfaces and the much more natural interfaces for whoever's on the end of prompting the system. Then we have the system itself, and I alluded to this just a few minutes ago, which is a system that, historically when you built an application, you wanted it to run predictably, not predictively, because you wanted the application to basically run the same way every time. Now we have systems that by design are taking a lot of different kinds of data versus heavily structured data. Think about databases. You'd have a database, and then you'd have like an ERP system or a CRM system or whatever it might be, and you'd run an application, the same way every time. Now, I've got lots of differently structured data, largely unstructured data and metadata. I train a model, I put it into an application interface. We just talked about the interface, and I want it to effectively predict something. The attention all you need was a language model, a large language model, not so large in this case, actually, that was predicting the next word and effectively recursively kind of iterating around the next set of words to generate a response that makes sense. In other words, it was creating a sentence, it was creating a paragraph based on the prompt that was given to it. It was predicting the word order based on context of a model that's been trained. So the systems now are using unstructured data, and they're using some degree of non-determinism versus determinism, and that, again, is a core difference of this era. And finally, of course, is the output. So we have the input, the prompt, we have the system, and we have an output, and the output is something generated. It can be, in the case of Midjourney, an image. In the case of GitHub Copilot, it can be code. In the case of AlphaFold and other things that are trained and built on top of that, it can be different kinds of genomic or peptide or RNA sequences. And of course, it can be text. Write me a paragraph about the history of Bellevue, as an example. And so that's the output, the generated response. And then inside, there's really just a set of macro building blocks. There's the infrastructure. Why is NVIDIA stock up 300% in the last year, right? Infrastructure. Lots of different flavors of that. People building their own kinds of chips. AMD just said they're going to have $2 billion next year of AI chip sales, as an example. And I don't mean to trivialize the infrastructure. Carver and others could speak to us all about the amazing evolution of the infrastructure. Then there's this concept of the models that you see, what I'm calling data sources and foundation models. Models aren't a bit of good unless they've got data that's trained them. But then you've got all these other techniques, going back to closed versus open, and all these other techniques around how do I prompt engineer to get the thing I want to get out of the model, again, whether it's an image, text, or code, or something else. Or if that doesn't get the job done, how much degrees of freedom do I have to fine-tune that model for my purposes? And maybe I got extra data that I can use to fine-tune that model, customize it, because I want the model to do stuff that's sort of legal contract related, or I want it to do something that's biologically related, for example. I can fine-tune the model to the extent the model lets me do that. And there's lots of different techniques. There's one that I think you're going to hear a lot more about in the next few years, which is called low-rank adaptation, or LoRa's. You'll hear more about that. And then it's like, well, sometimes the model and the fine-tuning of the model is not enough. I actually need to bring in outside data sources and be able to combine them. Hence, you see models and context as a service. And this is an area which is the term of art right now, the hot term of art in our world, is retrieval augmented generation. Unfortunate acronym, RAG, but that's what it is. I prefer context-aware retrieval, CAR, but okay, RAG's winning out right now in the vernacular. And then you ultimately have these application interfaces, and one of the things that we're seeing already is people want more constancy in whatever that interface layer is, but they want a lot of flexibility in terms of the models and the fine-tuning of the models and the other data sources and the retrieval augmented generation and the other things that will come. And so what will the new metaphor of human interfaces and machine interfaces be in a world where prompting is well beyond our imagination? So as we'll, I think, see over the next few years. There's one person who has some street cred on all this who seems to think, I agree with him, that the implication of this is that just like in every next generation of computational platform shifts, we've had more and more application variety. We went from hundreds of applications in the days of the PC to hundreds of thousands to millions, and that we are literally going to be in the hundreds of millions of unique applications. And one way to think about this is, why does anybody in this room want to have a seller's agent? The seller's agent works for the seller. By the way, the seller's agents are called Google and Facebook today. I want a buyer's agent. I want my own application that understands me, my identity, my interests, and my intent, and can work on my behalf, as a bot, to go find the things that I might be interested in buying and help me transact on them. So just one example, right, of why, Jensen Huang is suggesting here that the implication over time is going to be huge diversity in personalization and customization of models. Just like I want that to buy something, I also want that to recommend, different kinds of procedures from a health perspective based on my genetic, my proteomic, my transcriptomic makeup. Quickly here, because I'm rambling on a little too long, but I wanted to set the table on all this. There's a lot of money going into the space. This is only for the first 9 months on the 2023 number, so we think it'll be about $25 billion. This is specifically into Gen AI. And by the way, this is a year where overall venture is going to decline again by another 75 to 100 billion off of last year and the previous year's record highs. So, so within the context of the venture world being a little tougher out there, there's a lot of money going into generative AI. This is a more interesting slide, perhaps, because what it's saying is that there's a very small number of companies. I think if I click ahead actually here. There's a very small number of companies that are attracting the vast majority of the dollars. And those are largely the model companies. I am highly confident that that's going to change. Not that they aren't going to get a bunch of money more, and they will, but that it's going to be the vertical applications, the functional applications, the industry-specific applications that in the next set of years is where the capital is going to go to. And that you might see, more than expected, a pretty significant commoditization of the model layer as we build out the applications that are leveraging the model technology. Apple's actually been the most aggressive buyer of companies. They bought 3 of our companies over the last 6 years, and as you can see, others. But I think we're just getting started in this regard. And the point actually on this page is early days in terms of the M&A of the big players. But more interestingly is the degree to which they're all aggressively investing in and partnering with these next generation companies. Amazon and Google have invested in Anthropic, one of the model players, Microsoft, of course, and OpenAI. We could go down the list. Salesforce has actually invested in 10 of this group of companies. This group of companies is a selection of the 40 most compelling. This is determined by the broader venture community and determined by some data that we use from PitchBook, companies that are private companies in the intelligent application space. So you can see some of them are enabling technology companies, names you're probably familiar with. You heard about Databricks, Hugging Face. Again, these are all private companies. Companies like LangChain and Pinecone you may be less familiar with, but are kind of hot companies in our world. And then determined by how much money they've raised, some early, late, mid-stage companies. What's interesting about this group of companies is only 7 of these companies have been on the list all 3 years that we've done it. And only 11 of these companies are 2-time repeat winners from a prior year. So this is a very dynamic list of companies, and again, there's 60+ top VCs all around the world that are helping to curate this list. I think I've run out of time, so I'm not going to unpack some of the other findings from that, but I'll end with just this last thing, which is one of the truisms in our world is that, the customer doesn't care about your vision. Of course they do at some level. What they care about is that you're solving their problem. And we heard that loud and clear at our event 3 weeks ago, that there's lots of model complexity going on. There's model cocktails, model soups, ensemble models, lots of terms like that. And they were just getting started. One of the consulting firms that was there, we didn't allow too many of them in the room, but there was one, and they said they had 400 Gen AI projects going on. Only 20 of them are in production. So there's a long, long way to go. So we're really in the prototype phase, in the prototype to production journey. And finally, that there's more and more of a demand. Now people are realizing it, and it's why we think things like Microsoft 365 Copilot, which was actually made GA today, are going to be hugely successful, is because there is a hard ROI in many different realms, internal and external, to lots of companies that are going to be transformative because of these technologies. So with that, I'm going to invite Steve back up on stage and look forward to having conversations with you over the course of the next few days. Thank you so much for being here. Thank you for Discovery for putting this on. And let's all dig a little bit deeper on applied AI.
Really appreciate it. I think I neglected in my introduction that Matt is this year's chair and stepped in last year, and I'm really grateful to Matt for joining us as chair of the conference and the work that he and others have done to help ensure a successful gathering today. So thank you, Matt. Okay, a man who needs no introduction, George Gilder. You'll see George on stage even more than you'll see me, and I know that's a blessing to most of you. George, I was asking him backstage, I said, now, George, have you written 15 books? He said, no, 20. So I can't keep track. George is an amazing author, writer, thinker, technology futurist, and our co-founder and senior fellow. So I'm going to invite George up to the podium, and he will introduce our next speaker.
Well, Bob Metcalfe is, as we all know, the legendary figure who invented Ethernet. And since he's just come from the ether, which was the title of his incandescent column. He used to write for InfoWorld, but he's arrived from the ether above the United States and is here and ready to illuminate the subject of artificial intelligence as an expression, ultimately, I believe, of Metcalfe's law. Metcalfe's law is that essentially that the value of a network rises by the square of the number of users, nodes on the network. And this law has been manifest across the whole world of information technology that we've devoted COSM to for decades and is now going to gain a huge spur from the spread of graphene, a new materials revolution to revitalize all these information revolutions, which ultimately derive from the foundation of hardware. And Bob is fresh from the Turing Prize. He just won it in March, which is the most coveted prize in computer science. It's $1 million or something, and it's better than the Nobel Prize as far as we're concerned, because we believe that technology both spurs and embodies and enables new breakthroughs in science. So Bob is ready to talk about connectivity as the ultimate source of all these breakthroughs that Matt McElwain was describing and that we're experiencing daily. And thank you all for being here, and I'll be talking to you later. Thank you.
Howdy, y'all. I spoke with George the other day, and he told me what I was supposed to talk about, and I prepared my remarks, and then I just listened to his introduction, and it's completely different from what I agreed to talk about. But one thing's for sure, the Turing Prize is exactly 1,000,000,000. So you tell people you won the Turing Award, and they show some respect. When you mention the $1 million, they go crazy. This is the previous draft of my talk. This is the current draft. You all have probably heard that if a hammer is the only tool you have, everything looks like a nail. And my hammer is connectivity, for which I received this award, but about which I'm going to speak right now. Connectivity, by the way, just for definitional purposes, is the apparatus for moving stuff from A to B. Stuff like energy or mass, or in mostly my case, signals. The internet carries signals. It's connectivity. And I'm here to convince you that connectivity is a thing. It's more than a thing. It's the thing. It has proven over and over again to be a great place to start in the consideration of any system. The most important new fact about the human condition, I claim, is that we are now all suddenly connected. And by suddenly, I mean the internet began switching packets on October 29th, 1969, a little over 50 years ago. And it's had a very positive effect on the world, and also some negatives that I'll touch on. The most important new fact, therefore, worthy of your consideration. My favorite value that's been created by the internet has to do with extreme poverty. there's this great graph that I have to do more research into that shows the growth of extreme poverty going back 200 years. And it goes, for the first time in history, it goes like this. And I am aware of the difference between correlation and causality, but I believe that's causality at work, and a large value creator. But there are these pathologies that have arisen. And the pathologies arise because this bandwidth has come so quickly. In 50 years, we've gone from 0 to 5 billion users, 2/3 of the human race. And I claim that's so quick that we deserve some of the pathologies. For example, the first pathology of the internet was security. And I wrote the memo documenting the first instance of internet hack in Christmas of 1973. 2 high school students in Los Angeles got somebody's root password, and they didn't do too much damage. The next big pathology of the internet was pornography. The United States government almost shut down the internet because it's so good at carrying pornography. And then they passed a law called the Communications Decency Act in 1996. And as you know, there's now no more pornography on the internet. Then there's advertising. Those of us who built the internet in the early days were appalled when people started advertising on the internet. And we wanted to have it banned in some way. I don't know how you do that. But it took about a year or two before we discovered that advertising was not a pathology. It was the fundamental monetization engine of the internet. It helped us build the internet, and to this very day runs it. So pathologies come and go. We have some modern pathologies. They're likely to be a topic here in the next few days. The principal one I want to mention in passing is fake news. That's the big one. And the pairing of censorship. So that's a pathology that we're slowly working out. Another thing that occurred in the history of connectivity, the internet connectivity, are some reversals, which are really major reversals. The first one you've probably heard of, the Grosh-Moore reversal. Herb Grosh was an IBM executive who in the 50s had a law, just like me. And his law was that the cost of a computer went up as the square root of its power. The cost goes up as the square root. And therefore, a consequence is, and of course he was working for IBM at the time, bigger computers are better. Meanwhile, Gordon Moore is on the West Coast with his law, Moore's law, which basically ends up being small networked computers are better. And who won that? Moore won it. And as a result, Silicon Valley moved from 128 root 2 to 101 root 280 because of the belief in how big the computer should be, and small won out. Another reversal was noticed by Nicholas Negroponte. It's called the Negroponte switch. It was believed that what we were going to do is we were going to carry traffic on the internet locally on the copper that had been installed by AT&T, but for long distances we were going to go to microwave, either terrestrial or satellite. Negroponte noticed that it wasn't going that way at all. It went the other way. That is, we now go locally using Wi-Fi, and which is wireless, and the long haul is done with cables full of optical fibers. So that was a big reversal in the history of that connectivity. Let's see, and a really funny one. Marconi got his Nobel Prize, 1905 or so, for getting radio to go further and further and further over the hill by his Bologna villa across the Atlantic eventually. Marty Cooper, who, roughly speaking, invented the cell phone in 1973, he noticed that all progress in radio since Marconi was the other way around, getting radio to go shorter and shorter distances, thereby increasing frequency reuse and lowering power requirements. So those are reversals, and I only submit them because we're going to have some more, and it's good to be alert to the possibility that reversals are going to happen. So then came 2019. Something big happened in 2019. COVID. But something else happened in 2019. By huge coincidence, it was the 50th anniversary of the internet. It was almost as if we built the internet for COVID. Almost. So at the University of Texas, where I hang out, every single professor until COVID-19 said that they could never teach their courses over a remote video thing because they need to, touch their students and hug them and have rapid interaction. So video just wouldn't hack it. Of course, then COVID came along and every single course at the University of Texas is taught using Zoom. And it pretty much worked. We gave everybody a taste of what online, remote, video-based, collaborative video would do. We gave them a taste, and it's now playing out. It's going to take a decade or two to play out. We decide how much real estate we need and how much interaction we need. So I suggest that the acronym COVID be given a different meaning. Collaborative video. Now, there is this great radio that violates Cooper's Law, sort of. There was a pair of radios in 1977 were launched into space, and they're still there. In fact, they've left the solar system. They're now interstellar. And of course, the whole purpose of the space vehicles is to carry connectivity, radios. And so to this day, 40-some years later, we're still receiving radio signals from those two interstellar space vehicles. And that's a great example of, it's kind of an exceptional radio. I guess if you had a startup, the market wouldn't be very big for those radios. But, and then there's the neuron transistor paradox. And it's a connectivity paradox. And it relates, it's the one part of these remarks, George, that mentions AI. I'm going to touch on AI. I never promised to talk about AI. Why did you think I was going to talk about AI? I don't know. But in any case, there is this paradox. Neurons are huge, hunking, slow, old-fashioned kind of connection devices. And transistors are tiny and fast. And when I contrast the two, I'm talking about differences measured in the thousands and the millions and the billions. And so the neuron pales in significance next to the transistor. On the other hand, the things we build with neural nets, our brains, are smarter than the things we build with transistors. How can that be? We start out with such a huge advantage with our transistors, and then somehow we lose it. And the answer is very simple: connectivity. That is, it's the connectivity of those devices that determines their effectiveness. So that leads us to artificial intelligence. You knew we were going to get there. So AI is currently hot, you may have noticed. And neural nets are the way to go. Neural nets, neural networks of connectivity is key to AI. And so we have the story of chat. I've lost track of the numbers. I think chat 3 had 1.76 trillion connections in it. 1.76 trillion connections. They call them parameters, and they're analogous to synapses in the human nervous system. And it is now rumored that there's 100 trillion parameter model about to emerge. In fact, I asked the president of OpenAI about it. I asked him if it was going to be in chat 5 or something, 100 trillion. And he said, we'll see. And then I said, 100 trillion. Let's see, that's 10 to the 14th connections. But the human brain has a 10 to the 11th neurons, each of which has an average connectivity of 10 to the 4th. So the number of connections in the brain is a factor of 10 more than 100 trillion. So then I asked him, if we had 100 trillion, would we have AGI? And my connectivity-based analysis is we wouldn't. We're going to need a quadrillion connections to reach AGI, human intelligence. Now, George, I can go on and on. What would you like? I could tell you the story of Ethernet. 5 more minutes. So I got this Turing Award, and I am extremely grateful and humble about it. And I got it for Ethernet, the plumbing of the internet. And there's a surprise. There are actually 3 surprises in the internet, and let me just touch on those, and then I'll finish. That should be 5 minutes. So in 1973, Xerox Palo Alto Research Center decided to build arguably the first personal computer. Certainly the first cool personal computer was built at Xerox PARC. And I had just joined Xerox PARC from MIT, where I had put MIT on the then internet. It was called the ARPANET. And they had me do it again at Xerox, put Xerox on the internet by connecting computers into the packet switches there. And then the lab announced we're going to build this PC enabled by the Intel 1103 dynamic RAM. That's what really made that PC possible. And we all thought we needed a network to tie them together. For example, we were building a laser printer that was a page per second, 500 dots per inch. That's 20 megabits. So good old RS-232 wasn't going to hack it. So they gave the job to me, and I quickly recruited a Stanford grad student, David Boggs, and the 2 of us spent 2 years together. We were called the Boggsy twins for 2 years. And we built this Ethernet thing. And it had 3 principal features. First, it was a shared coaxial cable with devices that punctured it and connected to the semiconductor. So you could install a PC by puncturing the cable and connecting to it, and then putting voltages on it to embody your packets. So that was, they were called Gerald taps, and we got them from the cable TV industry. And then we needed a way of clocking the packets onto the cable and off, and we chose Manchester encoding. Every bit cell has the bit and its complement, so you're guaranteed that there's a transition in the middle, and that transition is the clock. So no more global clock needing synchronization. That was cool. And third, I spent a month at the University of Hawaii studying the Aloha network, a packet radio network. And we were reconfirmed in our belief that radio was not ready yet. It took 25 more years for the chips to arrive to make a local area network radio economic. So that's why we chose coax. But we did use Aloha Network's randomized retransmissions. That is, the stations had to take turns putting their packets on the network. And how would they do that? And we adopted the randomized retransmission method, which is you send. If you get an acknowledgement, great. If you don't, you randomize to avoid repeating the event, and then you try again. So the first Ethernet consisted of Gerald, Manchester, Aloha. And if anyone has looked at Ethernet recently, you'll notice that none of those 3 things is here anymore. They're gone. They went away a long time ago. What Ethernet did in an enduring way, and I'm almost done with my 5 minutes here, it did 3 different things. First, it delivered internet packets to the desktop. In the preceding networks, the packets would arrive at a big host computer, which would then run your app and communicate with you in characters Some of them are upper and lower case. They even had a red ribbon on some of the machines. Anyway, packets to the desktop so you could write apps like the World Wide Web. You could write them, getting access to the packet machinery of the internet in your PC. Second, the Ethernet ran at 2.94 megabits per second, which was 10,000 times, 10,000 times faster than what it replaced. So that was bandwidth abundance, and it made possible the uploading of cat pictures. And the third difference is Ethernet was standardized like the rest of the internet. So the three things, packets, abundance, and standardization, were the real gifts of Ethernet in 1973. And that has proliferated wildly over the intervening 50 years. What took them so long to give me that award? 50 years. Is that enough, George?
Well, you should answer a question.
Yeah, I could answer a question.
Any questions?
May I weigh in?
Yeah.
If you have questions, and we have a very limited amount of time, but there is a microphone over here, so if you have a question you'd like to ask, please step forward, and George, maybe you can ask Bob a question based on what you've heard.
Well, the connectome, as Sebastian sung of MIT, where you've got a new connection to MIT now, right?
I'm a research affiliate at MIT.
And you're also part of the Wolfram Institute, which is significant because Wolfram is going to be speaking to us, and he would not have agreed, I believe, if you were not going to be asking him questions. But any case, Sebastian Sung figured out that the human brain, the connections that in the human brain, all the axons and synapses and dendrites of the human brain take a couple zettabytes to map. And the whole global internet also takes a couple zettabytes to map. Do you think that's significant, these different connectomes, the connectome of a single human mind and the connectome of the global internet can be compared in any fruitful way, or am I being facile in saying that ultimately this means that AI will succeed to the extent that it's distributed as widely as human minds are distributed, that the whole idea of a singular AI is the fatal flaw of most of the models that we currently have for it?
I was being facile when I drew this model of a neuron and embodying all the connectivity of the brain and left out all that other plumbing that is in the connectome. So it's not purely connectivity. The neuron does some computing, and as does the transistor. So there's a comparison at that level. But this huge question you've just asked is, you should have warned me you were going to ask that question. I don't think there's any, I think the intelligence embodied in the internet is outgrowing the intelligence in the total human race, right?
That seems to be degenerating, right? Degenerative human.
Well, all these semiconductor firms are producing the brains of the artificial. I'm a connectivity guy. I'm not.
I
in
know.
1968.
Well, all right, Bob.
Wait a second.
Here's a question.
Let me say one thing. 1968, I wrote a thesis, an undergraduate thesis at MIT, whose title was "A Neuron Model and Some of Its Information Processing Capabilities." And my thesis advisor was Marvin Minsky. And I could tell that Marvin didn't think I was smart enough to do AI. So he sent me down the corridor to JCR Licklider's office, and I took up networking instead.
JCR Licklider prophesied the galactic computer network way back in 1955 or something. He's in some ways a father of the internet. Well, here's another question. Metcalfe's law, I think, applies to interconnected users. Although you began with devices, it's really users who are using devices. So when we have an Internet of Things, you know, there are all these trillion estimates of connectivity relate to the impending Internet of Things. And I believe that Metcalfe's law does not really apply to just everything that gets connected, that the things have to be connected to human minds. That's the source of that exponential you identified. Am I right about that?
I'd like to point out you named Metcalfe's law. Metcalfe's law was a slide in my drawer for 15 years before you discovered it and call it Metcalfe's law. And ever since then, I'm having to defend it everywhere I go, which I do. I am not caving on that. But it is not exponential. It's only quadratic.
Yeah,
so
quadratic.
Keep that in mind.
But I got that it's quadratic, but you still haven't answered my question.
I had a dinner with Gordon Moore once. He lectured me on Moore's law.
Yeah.
And he pointed out that Metcalfe's law had never been evaluated numerically, whereas his law...
I had Carver doing the research.
Well, yeah, maybe I should try to recruit Carver to make it.
You got to get Carver on board, Bob, or you're...
But I did write a paper, with a peer-reviewed paper, showing that my law applied to the first 10 years of Facebook.
Ah, all right. Well, however, you all should know that in Bob's Wikipedia, it offers a caution. It says that Metcalfe has also predicted a number of things that did not come true.
I think.
What do you think?
Yeah,
is that a correct statement, Bob?
Coming from you? When you write a weekly column, 605 words every Thursday night.
It was the greatest column ever written about technology. It was just a marvel. You all should go back and read his old InfoWorld. They're collected in a book.
The book is called Internet Collapses, and it's available on the internet, which didn't.
That was a great opening session. Can we hear it for Bob Metcalfe?
Thank you very much.
Thank you.